Welcome, friend. In this video, we'll explore how quantum physics explains the true nature of reality. Over the next 2 hours, we'll gently guide you through the principles that govern the tiniest particles in the universe, from wave-particle duality to entanglement and beyond. Each chapter is designed to help you learn something fascinating, while gradually drifting off to sleep. So get comfortable, relax your mind, and let the quiet strangeness of the quantum world carry you away. Chapter 1. What is quantum physics? Quantum physics is the branch of science that explains the behavior of the smallest particles in the universe. It describes how atoms, electrons, photons, and other subatomic particles interact, move, and exist. Unlike classical physics, which works well for everyday objects like planets, cars, or even grains of sand, quantum physics applies to things at atomic and subatomic scales, where the rules of the universe behave in entirely unfamiliar ways. To understand quantum physics, it's helpful to start with the history of why it became necessary in the first place. At the beginning of the 20th century, physics was considered a nearly complete science. Classical theories like Newton's laws of motion, Maxwell's equations for electromagnetism, and the laws of thermodynamics had explained almost everything observed in nature. Many believed that all the fundamental questions had been answered and that only minor refinements remained. But as scientists began studying certain phenomena in more detail, cracks in the classical framework started to appear. One of the first major problems arose from the study of blackbody radiation. A blackbody is a theoretical object that absorbs all radiation and emits energy solely based on its temperature. According to classical physics, the energy emitted by a blackbody should increase infinitely at shorter wavelengths, leading to what was known as the ultraviolet catastrophe. But experiments did not match this prediction. Instead, the emitted energy peaked at a certain wavelength and then dropped off, something classical theory couldn't explain. In 1900, the German physicist Max Planck proposed a bold solution. He suggested that energy isn't emitted continuously, but in discrete packets. These packets, or quanta, formed the basis of a new idea, that energy could only exist in specific amounts. Planck introduced a constant to describe this relationship, which became known as Planck's constant. His equation, E equals hf, described energy as being proportional to frequency, with h representing this fundamental constant. Although initially viewed as a mathematical trick, Planck's idea laid the foundation for a new understanding of energy and light. A few years later, Albert Einstein took Planck's idea further while studying the photoelectric effect. This effect occurs when light hits a metal surface and causes it to emit electrons. Classical physics predicted that increasing the brightness of light should release more electrons, regardless of the light's frequency. But that wasn't what happened. Experiments showed that only light above a certain frequency could cause electrons to be emitted, no matter how intense the light was. Einstein explained this by proposing that light itself is made of particles, now known as photons, and that each photon carried a specific amount of energy. If a photon didn't have enough energy, it couldn't knock an electron free. This explanation was a direct validation of Planck's quantum idea, and it earned Einstein the Nobel Prize in 1921. The notion that light could behave as both a particle and a wave was deeply unsettling at the time, but it turned out not to be limited to light. In 1924, the French physicist Louis de Broglie suggested that matter too could exhibit wave-like properties. This idea, initially speculative, was later confirmed by experiments showing that electrons could form interference patterns, behaviors previously associated only with waves, when passed through a double-slit apparatus. This confirmed that all particles could exhibit both wave and particle properties, depending on how they were observed. With these discoveries, a new branch of physics was forming, one that would require a complete rethinking of nature's laws. Throughout the 1920s, physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed the mathematical systems that would become quantum mechanics. Heisenberg's approach, known as matrix mechanics, focused on observable quantities and how they changed over time. Schrödinger introduced wave mechanics and the now famous wave function, a mathematical representation of a quantum system's possible states. Dirac later combined quantum theory with Einstein's special relativity and predicted the existence of antimatter. Despite appearing to follow different paths, the various approaches turned out to be equivalent, offering different ways to understand the same strange rules governing the quantum world. Together, they built the framework of modern quantum mechanics. At the core of this framework lies a collection of principles that defy our everyday experiences. In the quantum world, some physical properties are quantized. They can only take on certain discrete values. For example, the energy levels of an electron in an atom are not continuous. An electron must absorb or release a specific amount of energy to move between levels. This behavior is completely different from what we see in the macroscopic world. Another key principle is the idea of superposition. In classical terms, a coin is either heads or tails. But in the quantum world, until we observe it, a system can exist in a blend of multiple states. This isn't just a limitation of our knowledge, it's a fundamental property of the system. Only when we measure it does the system appear to choose a specific outcome. Even more surprising is the phenomenon of entanglement. When two particles become entangled, the state of one is directly related to the state of the other, no matter how far apart they are. Measuring one instantly gives information about the other. This strange link has been tested repeatedly and has always agreed with the predictions of quantum mechanics. Another core idea is uncertainty. Werner Heisenberg formulated a principle showing that certain properties, like a particle's position and momentum, cannot both be precisely known at the same time. The more accurately one is measured, the less precisely the other can be known. This isn't due to flaws in measurement tools. It's an intrinsic feature of quantum systems. To make predictions in quantum physics, scientists use wave functions, mathematical functions that describe the probability of finding a system in any given state. Unlike classical physics, which predicts definite outcomes, quantum physics deals with likelihoods. When we measure a system, we obtain one result, but before that, only probabilities exist. Many experiments have confirmed the principles of quantum mechanics with great precision. One of the most famous is the double-slit experiment with electrons. When electrons are fired at a barrier with two slits and no observation is made, they form an interference pattern, suggesting wave behavior. But if we place detectors to see which slit each electron goes through, the pattern disappears and the electrons behave like particles. This shift based on observation is one of quantum physics' most puzzling and compelling features. Other experiments, like those testing Bell's inequalities, have shown that entangled particles violate the predictions of classical physics, further confirming the accuracy of quantum theory. Quantum tunneling, another confirmed phenomenon, shows that particles can pass through barriers that should be impenetrable according to classical mechanics. This behavior plays a role in the fusion reactions powering the sun, and it's used in technologies such as tunnel diodes. Quantum physics isn't just theoretical. It's essential for much of modern technology. Transistors, the building blocks of all computers and smartphones, rely on the quantum behavior of electrons in semiconductors. Lasers operate based on electrons moving between quantized energy levels. Magnetic resonance imaging, or MRI, uses nuclear quantum properties to form detailed images of the human body. Even future technologies like quantum computing aim to harness phenomena like superposition and entanglement to solve problems beyond the reach of traditional machines. All of this is possible because quantum physics accurately describes how nature behaves at its most fundamental level. It departs from classical intuitions, but replaces them with a set of rules that are not only consistent and testable, but astonishingly precise. These rules may seem strange, but they are the foundation upon which much of our modern world is built. In summary, quantum physics is the study of how the universe operates at the smallest scales. It arose from the need to explain phenomena that classical theories could not, and it introduced concepts that challenge our common sense but have stood the test of time through experiment and application. Though abstract and often counterintuitive, quantum mechanics has proven to be one of the most successful and transformative frameworks in all of science. Chapter 2. Wave-particle duality. Wave-particle duality is one of the most fundamental and surprising principles in quantum physics. It refers to the fact that all particles, including light and matter, can exhibit both wave-like and particle-like properties, depending on how they are observed. This concept reshaped our understanding of the physical world and marked a major turning point in the development of modern physics. The story begins with light. For centuries, scientists debated whether light was a wave or a particle. In the 1600s, Isaac Newton proposed that light was made of particles, which he called corpuscles. Around the same time, Dutch physicist Christian Huygens argued that light was a wave, similar to ripples in water. These two competing theories coexisted for a long time, with experimental evidence supporting both at various points in history. In the 19th century, the wave theory gained ground. Experiments by Thomas Young in 1801 showed that when light passes through two narrow slits and hits a screen, it creates a pattern of bright and dark bands. This is known as an interference pattern and is characteristic of wave behavior. If light were just a stream of particles, it would form two bright spots behind the slits, not an intricate pattern. The wave model explained this beautifully, and for much of the 19th century, light was widely accepted to be a wave. But the particle model of light returned with a twist in the early 20th century. In 1905, Albert Einstein explained the photoelectric effect, the phenomenon in which light striking a metal surface can eject electrons from it. Classical wave theory could not explain why light below a certain frequency, no matter how intense, failed to knock electrons loose. Einstein proposed that light comes in discrete packets, or quanta, now called photons. Each photon carries energy proportional to its frequency. If the photon's energy isn't high enough, it can't dislodge an electron, regardless of how many photons are present. This observation could only be explained if light had particle-like properties. These two conflicting behaviors, wave-like interference and particle-like quantization, both seemed to be true. This was the first clear sign that the classical categories of wave and particle were no longer sufficient. Then came the astonishing idea that wave-particle duality might apply not just to light, but to matter as well. In 1924, French physicist Louis de Broglie proposed that electrons, which were firmly believed to be particles, might also exhibit wave-like properties. He suggested that every particle with momentum has an associated wavelength, now called the de Broglie wavelength. Though the idea was unconventional, it had deep theoretical implications and opened the door to a unified view of matter and energy. In 1927, this hypothesis was tested experimentally by Clinton Davison and Lester Germer in the United States. They observed that a beam of electrons scattered off a crystal of nickel produced a diffraction pattern, just like X-rays or visible light. This was conclusive proof that electrons could behave as waves. Around the same time, similar experiments by George Thomson, son of J.J. Thomson, who had discovered the electron, confirmed the same result. The dual nature of matter was no longer theoretical, it was observable. This discovery was revolutionary. Electrons, previously thought to be point-like particles, could behave like waves under the right conditions. These were not metaphors or approximations. The wave behavior was real and measurable. The implications were profound. It meant that all matter has a dual character, and what we observe depends on how we observe it. One of the most powerful demonstrations of wave-particle duality is the double-slit experiment. In this setup, a beam of particles, such as photons, electrons, or even larger molecules, is directed at a barrier with two slits. Behind the barrier is a detection screen. If one slit is open, particles pass through and form a single band. If both slits are open and no observation is made of which slit each particle passes through, an interference pattern emerges, indicating wave-like behavior. But if a detector is placed to observe which slit each particle goes through, the interference pattern disappears, and the particles form two distinct bands, as if they were little bullets. This shift in outcome, depending only on the presence or absence of measurement, is a defining characteristic of quantum mechanics. It challenges the idea that particles have definite paths or properties before we measure them. Instead, it suggests that the act of observation plays a role in determining the behavior of the system. The behavior of quantum objects is described mathematically by wave functions. These wave functions spread out over space and represent the probability distribution of finding a particle in a particular location. The wave function evolves according to Schrödinger's equation, a central formula in quantum mechanics. When no measurement is made, the particle's position is spread across many possibilities. When a measurement occurs, the wave function collapses, and the particle appears in one location. This probabilistic nature of quantum systems is not due to experimental imperfections or lack of knowledge. It is inherent in the mathematics and behavior of the system. Even with perfect information about the wave function, one cannot predict with certainty the exact outcome of a single experiment. Only the probabilities are known in advance. This dual nature applies not just to electrons or photons, but to all particles. In recent decades, scientists have demonstrated interference patterns using entire atoms and even large molecules composed of dozens of atoms. These results indicate that wave-particle duality is a general property of nature, not restricted to light or small particles. The larger the object, the shorter its wavelength, which is why everyday objects don't exhibit noticeable wave behavior. The wavelengths of macroscopic objects are so tiny that they become negligible for practical purposes. Despite its abstract nature, wave-particle duality has practical consequences. It is essential to understanding the structure of atoms, the behavior of electrons in solids, and the mechanisms behind technologies like electron microscopes and semiconductor devices. In electron microscopes, the wave nature of electrons allows scientists to achieve resolutions far beyond those of traditional light microscopes, revealing structures at the nanometer scale. Wave-particle duality also lies at the heart of quantum field theory, the framework that combines quantum mechanics with special relativity. In this theory, particles are viewed as excitations or quanta of underlying fields that permeate space. These fields vibrate and interact, and the resulting phenomena are interpreted as particles. In this sense, particles are localized expressions of field waves, reinforcing the duality in a more modern form. Understanding wave-particle duality has forced physicists to abandon classical intuitions and accept a more complex but accurate description of the universe. Rather than asking whether something is a particle or a wave, quantum physics teaches us that those labels are limited and context-dependent. What matters is the system's behavior under specific conditions and how we choose to measure it. This principle does not indicate a flaw in our logic or experiments, but rather reveals a deeper layer of reality, that becomes visible only at very small scales. Wave-particle duality isn't a contradiction. It is a broader understanding that nature doesn't fit neatly into classical categories. Instead, it follows its own rules, and those rules become visible when we ask the right questions in the right ways. Even though this behavior might seem foreign compared to the stability of the macroscopic world, it forms the foundation for all matter, energy, and interaction. Every atom in your body, every beam of light you've ever seen, and every material object around you owes its properties to this quantum duality. It is one of the most tested, confirmed, and powerful ideas in all of physics. By revealing that entities can act like both waves and particles, depending on how we observe them, wave-particle duality reshaped science. It opened new paths for inquiry and innovation and gave us tools to explore nature at its most fundamental level. In doing so, it continues to guide both theoretical research and practical technology, even a century after its discovery. Chapter 3. The Uncertainty Principle. The uncertainty principle is one of the most iconic and foundational elements of quantum physics. It fundamentally reshapes how we think about measurement, precision, and the very nature of physical reality at microscopic scales. First formulated by German physicist Werner Heisenberg in 1927, the uncertainty principle reveals a limit on how precisely we can simultaneously know certain pairs of physical properties of a quantum system. It is not just a technical limitation of instruments, but a built-in feature of how nature operates at the smallest scales. At its core, the uncertainty principle tells us that there is a trade-off in the precision with which we can measure two related quantities. The most commonly discussed example is the relationship between a particle's position and its momentum. Momentum is the product of mass and velocity, and in classical mechanics, both position and momentum can be measured with infinite precision if we use sufficiently accurate instruments. But quantum mechanics introduces a different framework, one where particles are described not by precise locations and speeds, but by wave functions, mathematical descriptions that represent probabilities. The wave function for a quantum particle, such as an electron, spreads out in space. It tells us where the particle is likely to be found if we perform a measurement, but it does not give a definite location until that measurement is actually made. The wider the wave function in space, the more uncertain the position of the particle. Conversely, if the wave function is narrow and concentrated in space, indicating a well-known position, then its spread in momentum becomes larger. This inverse relationship between the spread in position and the spread in momentum is exactly what the uncertainty principle describes. The formal expression of Heisenberg's principle is often written as an inequality. The product of the uncertainties in position and momentum must be greater than or equal to a small constant. That constant is Planck's reduced constant divided by 2 pi. Mathematically, it's stated as delta x delta p vice versa, where delta x is the uncertainty in position and p is the uncertainty in momentum. This means that the more precisely we try to determine a particle's position, the less precisely we can know its momentum, and vice versa. This relationship is not due to flaws in our equipment. Even with perfect detectors and zero experimental error, the uncertainty principle still applies. It is a direct consequence of the wave-like nature of particles. To understand why, consider a basic wave. A single frequency wave extends infinitely in space. It has a very well-defined wavelength and therefore a very well-defined momentum. But because it is spread out evenly, it has no particular location. It is completely delocalized. On the other hand, to localize a wave in space, to create a wave packet that has a specific position, you must combine many different frequencies. The result is a superposition of waves with slightly different momenta, leading to a wave packet that is localized but uncertain in momentum. This trade-off is not limited to position and momentum. The uncertainty principle applies to other pairs of quantities as well, such as energy and time, or angular momentum and orientation. In each case, there's a fundamental limit to how precisely both properties can be known at the same time. These relationships are all rooted in the mathematical structure of quantum mechanics, particularly in the way operators, mathematical tools that represent observable quantities, do not commute when applied in different orders. One of the most important consequences of the uncertainty principle is that it undermines the classical idea of determinism. In Newtonian physics, if we know the position and momentum of every particle in a system, we can, in theory, predict the future state of the system with perfect accuracy. But in quantum mechanics, such complete knowledge is impossible. We can only speak in terms of probabilities and likelihoods, not certainties. The future is not fixed, but governed by probability distributions that emerge from the wave function. This principle also has profound implications for our understanding of what it means to observe or measure something. In classical science, measurement is passive. We look at a system, and our observation reveals properties that were already there. In quantum mechanics, however, measurement is an active process that alters the state of the system. The uncertainty principle ensures that the more we try to pin down one property, the more we disturb its complementary property. One famous thought experiment that illustrates this is Heisenberg's microscope. Imagine trying to observe an electron using a microscope that uses light. To get a clear image, we might try to use high-energy photons with short wavelengths. These would allow us to resolve small details and determine the electron's position more precisely. But the high-energy photon would also transfer a large amount of momentum to the electron upon interaction, disturbing its velocity. If we use lower-energy photons to avoid disturbing the electron's momentum, the long wavelength of the light blurs our image and makes the position less precise. This dilemma exemplifies the unavoidable trade-off between knowing position and knowing momentum. In practical terms, the uncertainty principle sets hard limits on what we can know about systems like atoms, molecules, and subatomic particles. For example, it explains why electrons in atoms do not simply spiral into the nucleus. If an electron were confined to an extremely small region near the nucleus, its position would be very well defined, but its momentum, and thus its kinetic energy, would have to be extremely large, making such a state unstable. Instead, electrons exist in regions of space called orbitals, which represent the probability distributions of where an electron might be found. These orbitals are stable because of the delicate balance enforced by the uncertainty principle. The uncertainty principle is also essential to understanding the concept of zero-point energy, the idea that quantum systems never come completely to rest, even at absolute zero temperature. A quantum harmonic oscillator, such as a vibrating atom in a crystal lattice, retains a minimum amount of energy due to the constraints of the uncertainty principle. If it had zero energy, its position and momentum would both be exactly known, which the principle forbids. This residual energy is an unavoidable consequence of the quantum rules. In the realm of particle physics, the uncertainty principle provides insight into the fleeting nature of certain particles and phenomena. For instance, virtual particles, which briefly pop in and out of existence in quantum field theory, are permitted to violate conservation of energy for very short periods of time, a phenomenon allowed by the time-energy form of the uncertainty principle. These virtual particles contribute to observable effects, such as the Lamm shift in atomic energy levels and the Casimir effect between closely spaced plates. Although these implications may seem abstract, the uncertainty principle has very real and measurable consequences. Its predictions have been confirmed in countless experiments across decades of research. It plays a central role in quantum optics, where the manipulation of light at the quantum level requires precise control over complementary variables such as phase and amplitude. It also affects precision metrology, the science of making extremely accurate measurements by defining the ultimate sensitivity limits for instruments like atomic clocks and gravitational wave detectors. Understanding the uncertainty principle requires a shift in perspective. In the classical world, it makes sense to imagine that particles have exact positions and velocities at all times, even if we don't know them. But quantum physics forces us to accept a new kind of knowledge, one that is inherently probabilistic and based on what can and cannot be known simultaneously. This does not mean that the quantum world is chaotic or ill-defined. On the contrary, it follows strict rules and yields precise statistical predictions. But those predictions concern distributions and likelihoods, not fixed outcomes. The uncertainty principle is not a failure of measurement. It is not a technological limitation. It is a fundamental characteristic of how nature works. It is built into the mathematics of quantum theory and supported by a century of experimental validation. Rather than thinking of it as an obstacle, physicists have embraced it as a guide, a principle that shapes everything from the stability of atoms to the behavior of black holes. Even though the principle applies at scales far smaller than everyday life, it underlies the behavior of all matter and energy. It explains why the atomic world is structured the way it is, why electrons occupy specific energy levels, why chemical bonds form, and why the universe is not frozen into deterministic predictability. It introduces a kind of built-in fuzziness to reality, a reminder that even the most fundamental quantities in the universe come with a degree of inherent variability. In the vast landscape of physics, the uncertainty principle stands as a quiet but powerful reminder that knowledge itself has limits. And within those limits, new insights arise. Not from the ability to know everything, but from understanding the boundaries of what can be known. Chapter 4. Quantum Superposition. Quantum superposition is one of the most essential and puzzling concepts in quantum physics. It refers to the idea that a quantum system can exist in multiple possible states at the same time, and that only through observation does the system settle into a single, definite outcome. This principle is not just theoretical. It has been observed in countless experiments and is central to how particles, atoms, and molecules behave at the smallest scales. Yet it defies our common sense understanding of the world, where things appear to be in one state or another, not both at once. In classical physics, an object can be in only one state at a given time. A ball is either on the left side of a table or the right. A switch is either on or off. This is how we are used to thinking about the world, in terms of clear, definite conditions. But in the quantum realm, the behavior of particles is governed by wave functions, which describe the probabilities of different outcomes. Until a measurement is made, the system is not in one of those outcomes. It is in all of them at once, in a superposition. To understand superposition, it helps to consider how particles behave as waves. In quantum mechanics, particles such as electrons, photons, or atoms are associated with wave functions. These wave functions are not physical waves like water or sound, but mathematical functions that describe the likelihood of finding the particle in various states. When a particle can be in more than one state, its total wave function is formed by adding together the wave functions of all those states. This addition is not a random mixing, but a coherent sum where the individual components interfere with each other, much like overlapping ripples on a pond. The result of this addition is a new wave function that reflects the superposition of all possible states the particle could occupy. For example, if an electron can be in location A or location B, its wave function might include both locations. Before any observation is made, the electron is not just possibly in either A or B, it is truly in both, described by a wave function that includes both possibilities simultaneously. The probabilities of finding the particle in either location become real only when a measurement is made, causing the wave function to collapse into one outcome. One of the most well-known illustrations of superposition is the famous thought experiment called Schrödinger's cat, devised by Austrian physicist Erwin Schrödinger in 1935. The experiment describes a hypothetical scenario in which a cat is placed in a sealed box with a mechanism that has a 50% chance of releasing poison, depending on the decay of a radioactive atom. According to quantum theory, until the box is opened and the system is observed, the atom exists in a superposition of decayed and undecayed states. Consequently, the cat is considered to be both alive and dead, not in the sense of being partly alive, but in the sense of being in both states simultaneously. The point of Schrödinger's thought experiment was to highlight the strangeness of applying quantum rules to macroscopic objects. In practice, quantum superposition is difficult to observe directly at large scales because larger systems quickly interact with their environments in a process known as decoherence. This process causes the system to lose its quantum coherence and behave more classically. But at small scales, such as individual atoms, electrons, or photons, superposition is not only real but measurable. Experiments have repeatedly confirmed the existence of superposition. In one example, scientists send individual electrons through a pair of slits in a barrier. If no measurement is made to determine which slit the electron passes through, the electron behaves as though it goes through both slits simultaneously, creating an interference pattern on a screen. This pattern is the result of the electron's wave function being in a superposition of went through slit A and went through slit B. Only when detectors are placed to monitor the path does the interference disappear, and the electron behaves like a classical particle that went through one slit or the other. Superposition is not limited to position. Quantum systems can be in superpositions of other properties, such as spin, polarization, or energy levels. For instance, the spin of an electron, a quantum version of angular momentum, can point in different directions. Until it is measured, the spin is in a superposition of up and down. Once measured, the spin adopts a definite value. Before measurement, however, the particle's spin is in a genuine quantum mixture of both possibilities. This principle is also used in experiments with photons, where the polarization, the orientation of the light's electric field, can exist in a superposition of horizontal and vertical states. When passed through special devices like beam splitters or polarizers, the photons show interference effects that confirm the presence of superposition. These behaviors are not mere quirks of theory. They are experimentally verified and mathematically predictable. Quantum computers rely heavily on the principle of superposition. Unlike classical computers, which use bits that can be in one of two states, 0 or 1, quantum computers use quantum bits, or qubits, which can be in superpositions of both 0 and 1 at the same time. This allows quantum computers to perform certain calculations much more efficiently than classical machines by processing multiple possibilities in parallel. However, maintaining superposition in qubits is a major technical challenge, as they are extremely sensitive to noise and environmental interactions that cause decoherence. The phenomenon of superposition also plays a role in quantum chemistry and atomic physics. Electrons in atoms are described by wave functions that form standing wave patterns around the nucleus. These standing waves represent superpositions of possible positions and energies. The shapes and interactions of these wave functions determine how atoms bond with each other and form molecules. In chemical reactions, the transition states between reactants and products often involve superpositions of different bonding arrangements. Superposition is not simply a curiosity, it is at the heart of why quantum systems behave differently from classical ones. It introduces the idea that particles do not have definite properties until those properties are observed. This leads to questions about the nature of measurement, the role of observers, and the completeness of quantum theory. While these questions have sparked debate and various interpretations of quantum mechanics, the physical reality of superposition has never been in doubt. Physicists have also explored superposition using increasingly large systems. In recent years, researchers have managed to place small molecules consisting of dozens or even hundreds of atoms into superposition states. These experiments push the boundaries of how large a system can be while still exhibiting quantum behavior. Each new result provides stronger evidence that superposition is not limited to the microscopic world, although maintaining coherence becomes exponentially harder as the system grows. Despite its strangeness, the mathematics of superposition is precise and reliable. The wave function that describes a quantum system evolves deterministically according to Schrödinger's equation until a measurement is made. This evolution preserves the superposed states and allows interference patterns to emerge. The predictive power of this mathematics has been confirmed across countless experiments and underlies much of modern quantum theory. Understanding superposition requires letting go of the notion that physical systems must always be in definite, observable states. In the quantum world, potentialities coexist until the act of measurement reduces them to actualities. It is not that we simply don't know what state the system is in. Rather, the system truly exists in all its allowed states at once, each with a certain amplitude and phase that affect how it combines with others. The implications of this idea are vast. It suggests a level of indeterminacy in nature that is not due to ignorance or chaos, but is part of the fabric of reality. At the same time, superposition offers powerful tools for technology and scientific understanding. It enables precision control in fields like quantum optics and quantum information, and it plays a central role in the structure and behavior of atoms, molecules, and materials. The principle of superposition has been with quantum mechanics since its inception and continues to be one of the most fascinating and experimentally confirmed aspects of the theory. It shows that the quantum world is richer and more complex than the classical one we see every day. In that richness lies both mystery and possibility, a framework that not only explains how particles behave, but also offers the foundation for some of the most advanced and promising technologies of the future. Chapter 5: Quantum Entanglement. Quantum entanglement is one of the most intriguing and experimentally confirmed phenomena in modern physics. It describes a condition in which two or more quantum particles become linked in such a way that the state of one particle cannot be described independently of the state of the other, no matter how far apart they are. This connection persists even when the entangled particles are separated by vast distances. What happens to one immediately affects the other, not through any signal or force that travels between them, but as a consequence of the mathematics governing their shared quantum state. The concept of entanglement emerges naturally from the principles of quantum mechanics, particularly the idea of superposition. When two quantum systems interact and then separate, their wave functions can become entangled, meaning that their probabilities are no longer independent. Instead, they are described by a single, combined wave function that encodes correlations between the particles. These correlations remain even when the particles are no longer in contact. To grasp how entanglement works, it helps to consider a simple example involving particle spin. Spin is a fundamental quantum property akin to angular momentum. For electrons, spin can take one of two values, up or down. If two electrons interact in such a way that they must have opposite spins, their total spin state becomes entangled. This means that if one is measured and found to be spin up, the other will be spin down, and vice versa. But until a measurement is made, neither electron has a definite spin. Instead, they exist in a superposition of both possibilities, and the outcomes are strictly correlated. This entangled state does not depend on the distance between the particles. If one electron is sent to one side of the universe and the other to the opposite side, measuring the spin of one still determines the spin of the other instantly. This feature baffled even the founders of quantum theory. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper arguing that such behavior implied that quantum mechanics was incomplete. They suggested that there must be hidden variables, unknown factors that predetermine the outcome of each measurement. Einstein famously referred to entanglement as spooky action at a distance, expressing discomfort with the idea that one particle could instantaneously influence another. This led to the formulation of what became known as the EPR paradox, named after the authors of the paper. The paradox pointed out that if quantum mechanics were correct, it allowed for non-local effects, influences that traveled faster than light, seemingly violating the principle of causality. For decades, this question remained unresolved. Could there be hidden variables underlying quantum behavior, or was the theory truly non-local in the way it appeared to be? In the 1960s, physicist John Bell devised a way to test these competing ideas. He developed what are now called Bell inequalities, mathematical relationships that would be satisfied if hidden variables governed the outcomes of measurements. But if entanglement behaved as quantum mechanics predicted, then the inequalities would be violated. In the 1970s and 1980s, experimentalists such as Alain Aspect and his team in France conducted tests using entangled photons and polarization filters. The results consistently violated Bell's inequalities, confirming that the correlations observed in entanglement could not be explained by local hidden variables. These experiments have since been repeated many times, with increasing precision using photons, electrons, ions, and other quantum systems. The conclusion is now clear. Quantum entanglement is a real, measurable, and well-understood feature of nature. It does not involve faster-than-light communication or any transfer of information in the traditional sense. What it demonstrates is that the properties of entangled particles are not independent. They are part of a single, unified system, regardless of spatial separation. The act of measuring one particle doesn't send a message to the other. Rather, it reveals a relationship that was already built into their joint wave function from the start. Entanglement challenges our intuitions about separateness and independence. In classical physics, objects have their own properties regardless of what happens to other objects. But in quantum mechanics, the state of a system can be fundamentally relational. Two particles that were once entangled remain connected, not through a physical tether, but through the mathematical structure of their wave function. This interconnectedness has practical implications beyond foundational philosophy. Entanglement is central to the development of emerging technologies in quantum information science. One of the most promising applications is quantum communication, specifically quantum key distribution, or QKD. In QKD, two parties can share a secret encryption key by exchanging entangled particles. Because the correlations between the entangled particles are perfect and cannot be intercepted without disturbing the system, any attempt to eavesdrop becomes immediately detectable. This property offers the potential for unbreakable encryption. Another application is quantum teleportation, which sounds like science fiction but is firmly grounded in experimental physics. Quantum teleportation does not involve transporting matter from one place to another. Instead, it refers to the transfer of quantum states between distant particles using entanglement. By entangling two particles and performing a specific measurement on one of them, in combination with another particle whose state is to be teleported, it is possible to transfer the state of that third particle onto the remote entangled partner. This process requires both quantum entanglement and classical communication. It has been demonstrated many times in laboratories and is considered a foundational tool for building future quantum networks. Entanglement is also essential in the operation of quantum computers. In classical computing, bits are independent. Each bit can be either 0 or 1. In a quantum computer, however, qubits can be entangled with one another, allowing for complex correlations and parallelism that would be impossible with classical bits. This entanglement enables quantum algorithms to perform certain computations far more efficiently than their classical counterparts, offering the potential for breakthroughs in fields like cryptography, optimization, and materials science. On a more fundamental level, entanglement plays a role in our understanding of physical systems across many areas of physics. In quantum chemistry, entangled electrons determine the structure and stability of molecules. In condensed matter physics, entanglement underlies phenomena such as superconductivity and quantum phase transitions. In high-energy physics, entanglement is being explored in theories of black holes and the fabric of space-time itself. Some proposals even suggest that space-time geometry may emerge from patterns of entanglement in underlying quantum fields. While entanglement is a striking phenomenon, it does not allow for faster-than-light communication or violate the laws of relativity. Although the measurement of one particle's state instantly correlates with the state of its entangled partner, the outcomes are still random. This randomness ensures that no usable information can be transmitted faster than light. In other words, while the correlation is instantaneous, it cannot be used to send a message or cause an effect that breaks causality. This subtle but crucial distinction keeps quantum mechanics consistent with the principles of special relativity. The experimental confirmation of entanglement has been one of the great triumphs of modern physics. In recent years, researchers have entangled particles over distances of hundreds of kilometers, including between ground stations and satellites in orbit. These results not only support the theoretical foundations of quantum mechanics, but also open the door to global-scale quantum networks. The dream of a quantum internet, a network of entangled systems enabling ultra-secure communication and distributed quantum computing, is already under development. The fact that particles can remain entangled over such long distances without any classical connection or force between them speaks to the deeply non-local character of quantum mechanics. It shows that our classical intuitions about space, time, and separability are not fundamental features of the world, but approximations that break down at the quantum level. In this framework, information is not confined to single locations, but is spread out over entangled systems, forming correlations that defy classical logic but obey precise mathematical rules. Despite the counterintuitive nature of entanglement, it is now a well-understood part of the quantum world. Its predictions match experimental data with extraordinary accuracy, and its effects can be manipulated, harnessed, and controlled in the lab. What was once seen as a philosophical oddity has become a cornerstone of quantum technologies and a gateway to understanding the deeper structure of reality. As with many quantum phenomena, entanglement reminds us that our perceptions of how the world should behave are shaped by the macroscopic world we inhabit. But at the quantum level, the universe obeys rules that are richer, subtler, and more interconnected than our everyday experiences would suggest. By studying and applying those rules, we not only deepen our knowledge of the universe, but also develop new tools that may shape the future of science and technology. Chapter 6. The Observer Effect. The observer effect in quantum physics refers to the peculiar phenomenon in which the act of measuring or observing a quantum system directly influences the system's behavior. Unlike classical physics, where measurements reveal pre-existing values without altering the system, quantum mechanics presents a reality where observation itself plays an active role. This concept is not merely philosophical. It is backed by mathematical formalism and repeated experimental confirmation, making it one of the central and most intriguing features of the quantum world. To understand the observer effect, it's important to begin with how quantum systems are described. In quantum mechanics, a system is represented by a wave function, a mathematical function that encapsulates all the possible states the system can occupy. This wave function doesn't assign exact values to physical properties like position or momentum. Instead, it provides the probability of finding the system in various states. For example, a particle's position isn't a fixed coordinate, but a range of possibilities, each with a certain likelihood. As long as the system remains unobserved, the wave function evolves smoothly and deterministically over time according to Schrödinger's equation. This evolution keeps all possible outcomes in a delicate balance, forming what's known as a quantum superposition. But when a measurement is made, when an observer tries to determine a specific property like the position of an electron, this smooth evolution is interrupted. The wave function appears to collapse into a single definite state corresponding to the measurement outcome. This collapse is not described by Schrödinger's equation itself. Rather, it is introduced as a postulate of quantum mechanics. Before measurement, the particle exists in a superposition of states. After measurement, it has a definite value. The transition from the superposition to the single state occurs at the moment of observation, and the outcome is probabilistic, governed by the square of the wave function's amplitude for each possible result. A classic demonstration of this effect is the double-slit experiment. When particles such as electrons or photons are sent toward a barrier with two slits and no attempt is made to detect which slit they go through, they form an interference pattern on the screen behind the slits. This pattern is typical of waves, indicating that each particle somehow goes through both slits simultaneously in a superposition of paths. However, if a detector is placed at the slits to determine which slit each particle passes through, the interference pattern disappears. Instead, the particles behave like classical particles, forming two distinct bands behind the slits. The very act of observing which path the particle took changes the result. It's not that the detector disturbs the particle physically, though that can happen too. It's that the possibility of acquiring which path information destroys the interference pattern. This sensitivity to measurement suggests that observation is more than a passive process in quantum physics. It fundamentally alters the set of possibilities that the system can exhibit. In classical physics, you can observe a system without changing its state. Watching a planet orbit, for instance, has no effect on its motion. But in the quantum world, measurement and system are deeply intertwined. One important clarification is that the term observer in quantum mechanics does not necessarily refer to a conscious human being. In this context, an observer is any physical interaction that extracts information from the system. It could be a measuring device, a photon reflecting off a surface, or a particle detector. What matters is that a quantum system becomes entangled with its environment in a way that forces it into one of its possible states, thus collapsing the superposition. This transition from quantum indeterminacy to definite outcomes is sometimes called the measurement problem, and it has been the subject of extensive interpretation. The Copenhagen interpretation, which remains one of the most commonly taught frameworks, accepts the collapse of the wave function as a fundamental aspect of quantum theory. According to this view, the act of measurement causes the wave function to reduce to a single outcome, and there's no need to ask what the system was doing before observation. It simply had no definite properties. Other interpretations attempt to explain the observer effect in different ways. The many worlds interpretation, for example, denies that wave function collapse ever occurs. Instead, it proposes that all possible outcomes of a measurement actually happen, each in a separate branch of a continually splitting universe. In this view, measurement doesn't collapse possibilities. It reveals which branch you are on. While this removes the need for collapse, it introduces the idea of a vast multiverse where every possibility is realized. Still, other interpretations, such as decoherence theory, attempt to explain the appearance of collapse through the interaction of a quantum system with its environment. According to decoherence, the system's coherence, its ability to exist in a superposition, is rapidly lost as it becomes entangled with the surrounding environment. This process makes interference effects disappear and gives the appearance of classical outcomes, even though the wave function continues to evolve. Despite these differing viewpoints, the experimental fact remains that measuring a quantum system changes it. This is not limited to which path decisions in the double-slit experiment. It applies across a wide range of quantum systems. For instance, in quantum optics, the detection of a single photon collapses the light field into a different state. In atomic physics, measuring the energy level of an atom alters the distribution of electrons. In quantum computing, reading the value of a qubit collapses its superposition into a single binary state. This effect is not just a curiosity. It has real consequences for how experiments are designed and interpreted. Quantum cryptography, for example, relies on the fact that any attempt to measure a quantum key in transit will alter it, revealing the presence of an eavesdropper. In quantum computing, algorithms are carefully structured so that useful outcomes emerge only after a final measurement step. Until that point, the quantum system evolves in a superposition of computational pathways. It's also important to note that not all quantum systems undergo collapse in the same way. In weak measurements, for instance, only partial information is extracted from the system, allowing some coherence to remain. These measurements can reveal certain properties of a system without fully collapsing its state, offering a middle ground between pure quantum superposition and classical certainty. Such techniques are increasingly used in experimental quantum physics and quantum information processing. The observer effect also brings subtlety to the idea of reality in quantum physics. If a system doesn't have definite properties until measured, then what can we say about its state before observation? Are we to assume that reality itself is undefined until it is probed? Some physicists embrace this view, accepting that quantum properties are relational and only acquire meaning in the context of an interaction or observation. Others prefer to treat the wave function as a tool for prediction rather than a direct description of reality. In this view, quantum mechanics doesn't tell us what the world is, only what we can expect to observe. This pragmatic approach works well for calculations and experiments, but it leaves open deeper questions about the nature of existence at the quantum level. What's clear is that the observer effect places measurement at the heart of quantum physics. It is not merely a step at the end of an experiment. It is a defining act that brings quantum possibilities into classical reality. Without measurement, the wave function continues to evolve, existing in a cloud of probabilities. With measurement, a single outcome emerges, consistent with the statistical rules of quantum theory. This transformation is governed by precise mathematical laws and produces highly accurate predictions. Despite its counterintuitive nature, quantum theory has never failed a test and continues to match experiment after experiment with extraordinary precision. The observer effect, once a philosophical oddity, is now part of the operational framework of quantum science. Ultimately, the observer effect reminds us that, at the quantum level, knowledge and interaction are deeply connected. You cannot observe without participating. You cannot measure without influencing. This is not a flaw of the theory, it is one of its defining strengths, a reflection of the fact that at the smallest scales, the boundaries between system, instrument, and observer are blurred in ways that classical physics never imagined. Chapter 7. Quantum Tunneling. Quantum tunneling is a remarkable and well-established phenomenon that defies classical expectations. It allows particles to pass through energy barriers that, according to the laws of classical physics, they should not be able to cross. In the classical world, if a ball does not have enough energy to roll over a hill, it simply cannot get to the other side. In the quantum world, particles behave differently. Even if a particle does not possess enough energy to overcome a barrier, there is still a finite probability that it will be found on the other side. This is not a violation of energy conservation or a loophole in the laws of physics. It is a direct and predictable outcome of quantum mechanics. To understand quantum tunneling, it's important to revisit the idea that quantum particles are not simply tiny spheres moving along fixed paths. They are described by wave functions, mathematical constructs that spread out in space and contain information about where a particle is likely to be found. These wave functions are not confined to just the areas where the particle is allowed to be, according to classical rules. Instead, they can extend into regions that would normally be forbidden, such as through a potential energy barrier. In classical physics, if a particle does not have sufficient energy to climb over a barrier, it is reflected back. But in quantum mechanics, the wave function that describes the particle does not abruptly end at the edge of the barrier. Instead, it gradually decreases as it enters the barrier region. This means that the particle's probability of being found within the barrier is not zero. If the barrier is thin enough or the energy difference is small enough, the wave function can extend through the entire barrier and emerge on the other side. This effect is what we call tunneling. Quantum tunneling is not just theoretical, it has been observed and measured in a wide range of physical systems. One of the simplest examples involves electrons in a scanning tunneling microscope, or STM. In this instrument, a sharp metal tip is brought extremely close to the surface of a conducting material. When a small voltage is applied, electrons can tunnel through the vacuum gap between the tip and the surface, creating a measurable current. The intensity of this current depends sensitively on the distance between the tip and the surface, allowing the STM to map surface features with atomic scale resolution. This technique relies entirely on the principles of quantum tunneling. Tunneling also plays a vital role in nuclear physics. Inside the sun, hydrogen atoms undergo fusion to form helium, releasing enormous amounts of energy in the process. For fusion to occur, positively charged nuclei must come close enough for the strong nuclear force to overcome their electrostatic repulsion. However, at the temperatures found in the sun's core, the particles do not have enough kinetic energy, according to classical physics, to get that close. Quantum tunneling makes the difference. It allows protons to penetrate the energy barrier that separates them, enabling fusion to take place at a much higher rate than classical models would predict. In fact, without tunneling, the sun and all stars would burn far more slowly or might not shine at all. Quantum tunneling helps determine the rate of nuclear reactions in stars, influencing their lifetimes, luminosity, and evolution. This shows that a quantum phenomenon can have macroscopic consequences, shaping the structure and fate of entire galaxies. Another example comes from radioactive decay, particularly alpha decay. An alpha particle consists of 2 protons and 2 neutrons, essentially a helium nucleus. Inside heavy atomic nuclei like uranium, alpha particles are trapped in a potential well created by the strong nuclear force. Classically, they should remain confined forever. But quantum mechanics allows these alpha particles to tunnel through the potential barrier and escape from the nucleus, leading to radioactive decay. The rate at which this happens can be calculated using tunneling probabilities and matches experimental observations with great accuracy. Tunneling also plays an important role in modern electronics. In tunnel diodes, for example, electrons can tunnel through a narrow region of insulating material between two conductors. This tunneling effect allows the diode to operate at very high speeds and enables unique current voltage characteristics. Such components are used in high-frequency oscillators, amplifiers, and other specialized circuits. In flash memory used in smartphones and USB drives, electrons tunnel through insulating layers to store information. These applications demonstrate how tunneling is not only a curiosity of the subatomic world, but a useful tool in advanced technology. At the nanoscale, where dimensions are on the order of a few nanometers or less, tunneling becomes increasingly important. In field effect transistors, the building blocks of modern digital electronics, reducing the size of components eventually leads to quantum tunneling between regions that are supposed to be isolated. This can create leakage currents and affect the reliability of circuits. Engineers designing ever smaller chips must account for quantum effects like tunneling to ensure devices work as intended. The mathematical framework for quantum tunneling is well understood. Schrödinger's equation, which governs the evolution of quantum systems, allows for solutions where the wave function penetrates into classically forbidden regions. The likelihood of tunneling depends on several factors: the width and height of the potential barrier, the energy of the particle, and the particle's mass. Lower barriers, thinner barriers, and higher particle energies all increase the probability of tunneling. Conversely, heavier particles are less likely to tunnel than lighter ones. Although the mathematics of tunneling is straightforward in many cases, the consequences are often surprising. It forces us to reconsider what it means for a particle to be confined or trapped. In classical physics, confinement is absolute. If the particle lacks energy, it stays put. In quantum mechanics, confinement becomes probabilistic. There is always a small chance that a particle will appear somewhere it shouldn't be, not by violating energy conservation, but because energy in quantum physics is governed by probability amplitudes, not certainties. Tunneling is also involved in biological processes, although research in this area is ongoing and complex. For example, in the enzyme-catalyzed reactions that drive metabolism, there is evidence that quantum tunneling enables certain hydrogen atoms to move between molecules more efficiently than would be possible through classical means. These reactions are fundamental to life and suggest that quantum mechanics plays a subtle yet crucial role even in biological systems. In recent years, tunneling has found new relevance in the study of quantum computing. In certain types of quantum computers, such as quantum annealers, the system explores a landscape of possible solutions by tunneling between different energy minima. This allows the computer to search for optimal solutions in complex optimization problems that would be difficult or impossible for classical computers to solve in a reasonable time. While quantum computing is still an emerging field, tunneling is likely to remain a key principle in its development. One particularly fascinating aspect of tunneling is that it suggests time itself behaves differently at quantum scales. When a particle tunnels through a barrier, it appears on the other side without having traversed the space in the usual sense. The time it takes for a particle to tunnel has been the subject of debate and investigation for decades. Some interpretations suggest that tunneling occurs instantaneously, while others calculate finite tunneling times using subtle experimental techniques. Regardless of the interpretation, the particle's behavior cannot be explained by classical motion through space. Tunneling also raises interesting questions about determinism and randomness. Since the tunneling process is governed by probabilities, it is impossible to predict exactly when a given particle will tunnel through a barrier. Instead, we can only describe the average behavior of a large number of particles. This probabilistic nature reflects the broader framework of quantum mechanics, where uncertainty and chance are not artifacts of ignorance, but intrinsic features of reality. Despite its counterintuitive implications, quantum tunneling has become one of the most precisely verified predictions in quantum mechanics. Its effects are not only observable but calculable, and the agreement between theoretical predictions and experimental measurements is consistently strong. Tunneling has been tested in laboratories, built into instruments, observed in nature, and embedded in the technologies that define our modern world. By allowing particles to do what seems impossible, quantum tunneling reveals the depth and subtlety of the quantum world. It shows that our everyday experience, governed by classical physics, is only an approximation of a richer and more complex underlying reality. The rules at quantum scales differ, but they are coherent, consistent, and incredibly powerful. In the grand tapestry of physics, tunneling is a thread that connects the invisible actions of subatomic particles to the visible workings of stars, technologies, and possibly even life itself. It is not a violation of physical law, but a manifestation of how those laws operate under different rules that continue to surprise, inspire, and challenge our understanding of the universe. Chapter 8. The role of probability in quantum mechanics. Probability lies at the heart of quantum mechanics. Unlike classical physics, which deals in certainty and predictability given initial conditions, quantum mechanics operates on a fundamentally probabilistic framework. It does not allow us to determine the exact outcome of a measurement in advance. Instead, it tells us the probability of each possible result, even if we know everything about the system's current state. This use of probability is not due to ignorance or lack of precision. It is built into the very laws that govern the quantum world. In classical physics, the behavior of a system can be described in terms of definite quantities like position, velocity, and force. If one knows the starting position and velocity of a ball, Newton's laws can be used to predict where it will be at any future time. This determinism formed the foundation of physics for centuries and worked extraordinarily well for everything from planetary motion to engineering and mechanics. Probability in classical physics only entered the picture when systems became too complex to follow in detail, such as in statistical mechanics. But in principle, if all variables were known, future outcomes could be calculated with certainty. Quantum mechanics introduced a different approach. Instead of predicting exact results, it calculates the likelihood of each possible outcome using a mathematical object called the wave function. The wave function is a complex valued function that contains all the information about a system's quantum state. From this function, physicists can determine the probabilities associated with different measurements. For instance, if an electron is described by a certain wave function, the square of the wave function's amplitude at a particular position gives the probability density of finding the electron there when a measurement is performed. This probabilistic framework does not arise from experimental limitations or lack of knowledge. It is not that the electron has a definite position that we simply don't know. Rather, the electron does not have a definite position at all until it is measured. It exists in a spread of potential locations, and the wave function only tells us how likely we are to find it in each one. This approach was formalized in the early 20th century by physicists such as Max Born, who interpreted the square of the wave function's amplitude as a probability density. This interpretation, sometimes called the Born rule, became a cornerstone of quantum mechanics. It shifted the role of physics from predicting outcomes with certainty to describing statistical patterns over many trials. When the same quantum experiment is repeated many times under identical conditions, the results follow the probabilities predicted by the wave function. One of the simplest examples illustrating the role of probability in quantum mechanics is the double-slit experiment. When particles like electrons or photons are fired at a barrier with two slits, they create an interference pattern on a screen behind the barrier, evidence of wave-like behavior. If the experiment is performed one particle at a time, the individual detection events appear randomly across the screen. But as more and more particles are sent through, a clear interference pattern emerges. The wave function describes the probabilities of each particle landing at a given location, and the pattern aligns with these probabilities. No individual outcome is predictable, but the statistical distribution follows a well-defined form. In the quantum world, probability is not confined to positions alone. It governs all measurable quantities, including momentum, energy, spin, and polarization. For each observable, quantum mechanics defines a set of possible outcomes and assigns probabilities to each. These probabilities are not arbitrary. They emerge from the wave function's structure and the mathematical operators associated with each physical quantity. Even when a system is in a well-defined state for one observable, it may still have a probabilistic distribution for another. For example, if a particle's momentum is precisely known, its position becomes completely uncertain, and vice versa. This behavior is a manifestation of the Heisenberg uncertainty principle, which limits how much information we can have about certain pairs of observables. The uncertainty is not just in our measurements. It reflects the actual behavior of the quantum system. Another striking feature of quantum probability is that it allows for interference between different possible outcomes. Unlike classical probabilities, which simply add together, quantum probabilities can interfere constructively or destructively. This interference arises from the wave-like nature of the wave function and leads to effects like the dark and bright fringes in interference patterns. In mathematical terms, quantum amplitudes are complex numbers, and their phases can lead to cancellation or reinforcement of probability amplitudes when combined. This interference of probabilities has profound implications. It means that the history of a quantum system can influence its future behavior in ways that classical physics does not allow. The famous quantum eraser experiment, for instance, shows that erasing witch path information after a particle has passed through a double-slit apparatus can restore the interference pattern, even though the particle's trajectory was already recorded. Such experiments highlight how quantum systems do not simply follow paths through space and time, but instead evolve through probability amplitudes that include all possible histories. The probabilistic nature of quantum mechanics also changes how we understand measurement. When we measure a quantum system, we obtain a definite result, but this outcome is selected from a range of possibilities dictated by the wave function. The act of measurement causes the wave function to collapse to a specific state corresponding to the observed result. Before the measurement, the system was in a superposition of possibilities. Afterward, it is in a single state. The transition is instantaneous and unpredictable in terms of specific outcomes, though it follows strict statistical rules when repeated many times. The randomness inherent in quantum mechanics is fundamentally different from classical randomness. In classical physics, randomness often arises from incomplete information. If you flip a coin, the outcome appears random. But in principle, if you knew all the forces and initial conditions, you could predict the result. In quantum mechanics, no such hidden knowledge exists. The unpredictability is intrinsic. Even with a complete description of the system, the individual outcomes of measurements remain probabilistic. This raises deep questions about the nature of reality. Is the world inherently probabilistic, or is there a deeper layer of reality governed by hidden variables? Various interpretations of quantum mechanics attempt to address this. Some, like the Copenhagen interpretation, accept probability as fundamental. Others, such as the de Broglie-Bohm theory, introduce hidden variables that restore determinism at the cost of adding non-local dynamics. Still others, like the many worlds interpretation, suggest that all possible outcomes actually occur in parallel universes, and probability reflects the branching of these worlds. Despite these philosophical differences, all interpretations agree on the practical use of probability in quantum mechanics. They make the same predictions for the outcomes of experiments and rely on the same mathematical structure. Whether probability is a reflection of our knowledge or a feature of the universe itself, it remains central to how quantum systems behave and how we interact with them. The use of probability in quantum mechanics has not hindered the development of precise and powerful technologies. On the contrary, it has enabled them. Devices like lasers, MRI scanners, atomic clocks, and quantum computers operate based on probabilistic quantum principles. In quantum cryptography, the randomness of quantum measurements provides secure encryption keys that cannot be predicted or intercepted. In quantum sensing, fluctuations in probabilities are used to detect tiny variations in physical quantities with extreme sensitivity. Even in the most controlled quantum systems, such as trapped ions or superconducting qubits, probability governs every operation. Quantum gates, used to manipulate qubits in quantum computing, operate on superpositions and produce outcomes that are read out probabilistically. Entire algorithms are designed around the idea of maximizing the probability of obtaining the correct result, rather than computing it deterministically. Moreover, in fields like quantum thermodynamics and quantum chaos, the probabilistic nature of quantum mechanics plays a crucial role in understanding how systems transition between quantum and classical behavior. These studies reveal how classical behavior emerges from quantum rules when systems involve large numbers of particles and interactions with an environment, a process known as decoherence. Probability also helps explain why quantum mechanics aligns with classical physics in the macroscopic world. While individual quantum events are unpredictable, the law of large numbers ensures that averages and statistical patterns become reliable at larger scales. This is why classical mechanics remains accurate for most everyday applications, even though it is technically an approximation of quantum rules. Ultimately, the role of probability in quantum mechanics is not a weakness of the theory. It is one of its defining features. It reflects the richness and subtlety of the quantum world, where outcomes are not fixed in advance but emerge from a tapestry of possibilities. These probabilities are not guesses or estimates. They are precise, calculable, and testable quantities that have been confirmed by experiments to extraordinary accuracy. By embracing probability as a fundamental part of physical law, quantum mechanics provides a deeper and more nuanced understanding of nature. It shows that the universe is not a clockwork machine grinding predictably forward, but a dynamic system where potential and actual coexist, governed by rules that allow uncertainty and certainty to live side by side. Chapter 9. How Quantum Physics Changed Our View of Reality. Quantum physics has revolutionized our understanding of the natural world in ways that are both profound and far-reaching. Before its emergence in the early 20th century, science was grounded in the principles of classical physics, a framework that described the universe as a deterministic, continuous, and predictable system. Objects were thought to have precise positions and velocities, and every event was believed to be the result of prior causes following well-defined laws. The development of quantum mechanics disrupted this worldview entirely, replacing it with a model that emphasizes uncertainty, probability, and the fundamental limits of knowledge. At the core of this shift is the realization that particles do not behave like tiny solid objects, as once believed. Instead, quantum entities, such as electrons, photons, and atoms, exhibit behaviors that defy classical explanation. They can exist in multiple states at once, interfere with themselves, become entangled across vast distances, and exhibit randomness at a fundamental level. These characteristics challenge our traditional notions of what it means for something to exist or to be in a state. One of the earliest and most dramatic changes in perspective came from the discovery of wave-particle duality. Classical physics held that light was a wave and matter consisted of particles. But experiments showed that light can behave like a stream of particles, and matter can exhibit wave-like interference patterns. This dual behavior suggests that our classical categories are inadequate and that the underlying nature of reality is more nuanced than any simple label. Quantum mechanics replaced the idea of absolute certainty with a statistical framework. Rather than predicting the precise outcome of an event, the theory provides the probabilities of different possible outcomes. The wave function, a central concept in quantum mechanics, does not give definitive answers. It gives probability amplitudes. When squared, these amplitudes yield the likelihood of finding a particle in a given state. This change means that the future is not determined in the strict classical sense. Even with perfect knowledge of a system's wave function, the outcome of a measurement cannot be predicted with certainty. Only the probabilities of various results can be known. This probabilistic nature of quantum mechanics has forced physicists to rethink the role of measurement and observation. In classical physics, measuring a system simply reveals what was already there. But in quantum mechanics, measurement plays an active role. The system exists in a superposition of states until a measurement is made, at which point the wave function collapses into a specific outcome. This collapse is not a gradual process. It happens instantaneously, and it introduces an element of indeterminacy into the fabric of reality. The implications of this are far-reaching. For one, it calls into question the idea of an objective, observer-independent reality. In quantum mechanics, the properties of a system may not be well defined until they are measured. This raises challenging questions about the nature of existence. Does a particle have a position before we look at it? Is the universe fundamentally relational, with outcomes shaped by the context in which measurements occur? Quantum entanglement adds another layer to this transformation of our worldview. When particles become entangled, their states are linked in such a way that measuring one immediately determines the state of the other, regardless of the distance between them. This instantaneous correlation cannot be explained by any signal traveling through space. It suggests that the universe is non-local, that events separated by space can be intimately connected in a way that classical physics cannot account for. While this does not allow faster-than-light communication or violate causality, it does force us to reconsider the principle of separability that underlies much of classical science. The philosophical consequences of entanglement and non-locality are still being debated, but the experimental evidence is clear. The violations of Bell's inequalities demonstrate that no local hidden variable theory can reproduce all the predictions of quantum mechanics. Reality, it seems, does not adhere to classical constraints. It follows rules that are more abstract, less intuitive, and deeply interwoven with the act of observation itself. Quantum mechanics also redefines the concept of information. In classical systems, information is straightforward. A bit is either 0 or 1, a particle is either here or there. But in quantum systems, information can exist in superpositions, and operations on quantum bits, or qubits, can affect multiple states simultaneously. This leads to phenomena like quantum computing, where computations are performed across a vast landscape of possibilities in parallel. It also leads to quantum cryptography, where the laws of physics guarantee the security of information transmission. In classical thermodynamics, information was not typically considered a physical quantity. But quantum theory has shown that information is intimately tied to the physical state of a system. Concepts such as quantum entropy and the no-cloning theorem, an axiom that states it is impossible to create an identical copy of an unknown quantum state, demonstrate that information in the quantum world behaves very differently. These principles have opened up entire fields of research, including quantum information theory and quantum communication. Perhaps one of the most transformative effects of quantum physics is the way it challenges our sense of determinism. In the classical view, given enough data, we could predict any future state of the universe. This notion, championed by thinkers like Laplace, painted a picture of a clockwork cosmos where the future was merely a calculation away. Quantum mechanics replaced this certainty with a fundamental unpredictability. No matter how much we know about a system, some aspects of its future behavior remain inherently unknowable until they are observed. This does not mean that the universe is chaotic or lawless. Quantum mechanics is extraordinarily precise and reliable in its predictions when it comes to statistical ensembles. It allows physicists to make accurate predictions about atomic spectra, chemical reactions, and the behavior of materials. It underlies the technology of semiconductors, lasers, superconductors, and atomic clocks. But at the level of individual events, the theory does not yield certainty, only likelihood. This shift has had a profound impact not only on science, but on how we think about knowledge, reality, and the limits of human understanding. Quantum mechanics does not tell us what things are in the traditional sense. Instead, it tells us what we can know about things, and how that knowledge is affected by our interactions with the systems we study. The mathematical formalism of quantum mechanics is among the most successful in the history of science. The equations work. The predictions match experiment after experiment with stunning accuracy. But interpreting what the equations mean has been a subject of debate for over a century. The Copenhagen interpretation, the many worlds interpretation, the de Broglie-Bohm pilot wave theory, and objective collapse models all attempt to explain what lies beneath the formalism. Each carries different implications for how we understand time, space, and the act of measurement. Regardless of interpretation, the practical consequences are clear. Quantum mechanics has permanently changed our view of reality. It has shown us that the universe is not simply a collection of objects moving through space, but a dynamic interplay of probabilities, interactions, and relationships. What we observe depends on how we observe. What exists may be inseparable from the context in which it is examined. Even as we use quantum theory to build technologies and probe the foundations of matter, we continue to wrestle with its meaning. The insights it offers are not just scientific but philosophical. They push us to consider the boundaries of objectivity, the role of knowledge in shaping outcomes, and the possibility that the universe is, at its core, more fluid and interconnected than we ever imagined. In that sense, quantum physics is not merely a theory about small particles, it is a new lens through which to view the entire fabric of reality. It teaches us that the universe is governed not by certainty, but by possibility. And within those possibilities lies a world that continues to challenge our understanding and expand our imagination. Chapter 10. Quantum theory in the real world. Quantum theory is often thought of as a subject reserved for laboratories, particle accelerators, or chalkboards filled with complex equations. While its principles may seem abstract or confined to the realm of theoretical physics, quantum mechanics is not just a set of ideas. It is the foundation of much of the technology we use every day. From smartphones to medical imaging, and from energy generation to secure communications, quantum theory has moved beyond the blackboard and into the real world in countless ways. At its core, quantum mechanics describes how matter and energy behave at the smallest scales. The strange and counterintuitive principles it reveals, such as superposition, entanglement, tunneling, and the observer effect, are not limited to atoms and particles in isolation. They underpin real systems, govern real materials, and influence real devices. The remarkable accuracy and reliability of quantum predictions have enabled the development of technologies that depend on controlling and understanding these very small systems. One of the most direct applications of quantum theory is in semiconductors. These materials are the backbone of all modern electronic devices, from computers and smartphones to LED lights and solar panels. The behavior of electrons in semiconductors cannot be understood using classical physics alone. It is governed by the quantum nature of energy levels and the band structure of solids. Electrons in semiconductors occupy energy bands, and their ability to jump between these bands, governed by quantum principles, determines whether a material behaves as a conductor, insulator, or something in between. Devices like transistors, which control the flow of electrical current, rely on precise manipulation of these quantum properties. Lasers also owe their existence to quantum theory. The word laser stands for light amplification by stimulated emission of radiation, a process that depends on electrons in atoms absorbing and emitting photons in quantized amounts. When atoms are excited to higher energy levels, they can emit photons in a controlled and coherent manner when stimulated by incoming light of the same frequency. This cascade of emissions produces the narrow, powerful beam of a laser. Today, lasers are used in everything from barcode scanners and DVD players to surgical instruments and fiber optic communication systems. Another major application of quantum mechanics is in the field of medical imaging. Magnetic resonance imaging, or MRI, is a powerful diagnostic tool that creates detailed images of the inside of the human body. It is based on the quantum property of nuclear spin. When placed in a strong magnetic field, the spins of certain atomic nuclei, such as hydrogen and water molecules, align with the field. Radio frequency pulses then disturb this alignment, and as the spins return to equilibrium, they emit signals that are detected and used to construct images. The entire process relies on precise quantum interactions between particles and fields, and it has revolutionized the field of non-invasive medicine. Atomic clocks represent another triumph of quantum precision. These clocks keep time by measuring the frequency of radiation associated with transitions between energy levels in atoms, typically cesium or rubidium. Because these transitions occur at extremely stable and well-defined frequencies, atomic clocks can keep time with extraordinary accuracy, losing only a second every millions of years. Such precision is essential for technologies like GPS navigation, which relies on the synchronization of signals from satellites orbiting Earth. Without quantum mechanics, global positioning systems would simply not function as we know them. Quantum tunneling, another fundamental quantum effect, also finds real-world applications. In tunnel diodes, electrons are able to pass through energy barriers that would be insurmountable in classical physics. This behavior is exploited in high-speed and low-power electronic circuits. In flash memory, used in devices like USB drives and solid-state hard drives, tunneling is used to trap or release charge in memory cells, allowing data to be written and stored. Even nuclear fusion in stars, including our Sun, depends on quantum tunneling. Without it, the positively charged nuclei in hydrogen atoms could never get close enough to fuse and release energy, and life on Earth would not exist. The field of quantum optics explores how individual particles of light, photons, can be manipulated, measured, and used in applications. Devices like photodetectors, solar cells, and quantum light sources rely on the ability to understand and engineer quantum states of light. Photon-based quantum communication systems are now being developed to allow secure transmission of information through quantum key distribution. This method uses the principles of quantum uncertainty and entanglement to ensure that any eavesdropping attempt would be detectable. Unlike classical encryption, which can be broken with sufficient computing power, quantum encryption is theoretically secure based on the laws of physics. Perhaps the most exciting frontier for quantum theory in the real world is quantum computing. Unlike classical computers that store and process information in binary bits, either 0 or 1, quantum computers use qubits, which can exist in superpositions of states. This allows quantum systems to perform complex calculations in parallel, potentially solving problems that would be intractable for classical machines. Tasks like factoring large numbers, simulating molecular interactions, and optimizing complex systems may be vastly accelerated by quantum computing. While still in early stages of development, working quantum processors have already demonstrated capabilities such as entanglement-based logic gates and quantum error correction, proving that the underlying principles work outside of theory. Quantum sensors are another emerging area where theory meets application. These devices exploit quantum phenomena such as superposition and entanglement to measure physical quantities with extreme sensitivity. They can detect tiny changes in magnetic and electric fields, gravitational forces, and acceleration. Applications range from medical diagnostics and geological surveying to navigation in environments where GPS signals are unavailable. Cold atom interferometers, which use clouds of ultra-cold atoms in free fall, are being developed as ultra-precise accelerometers and gravimeters for use in both research and industry. Beyond individual devices, quantum theory is also influencing how we build and model materials. Quantum chemistry, which uses quantum mechanical principles to calculate the properties of molecules, allows scientists to predict how new compounds will behave without the need for extensive physical testing. This is crucial in drug development, material science, and nanotechnology, where understanding atomic interactions leads to innovations in medicine, energy storage, and manufacturing. In the realm of energy, quantum mechanics is helping to improve technologies such as photovoltaics and superconductors. Understanding how electrons move through materials at the quantum level enables the design of more efficient solar cells and energy harvesting systems. Superconductors, which carry electric current without resistance at low temperatures, rely on quantum pairing of electrons into what are called Cooper pairs. These materials hold promise for power transmission, magnetic levitation, and quantum computing hardware. Even biological systems are now being studied through a quantum lens. Research into quantum biology explores whether quantum effects such as coherence and tunneling may play roles in processes like photosynthesis, bird navigation, and enzyme function. While still an emerging field, these studies suggest that life itself may take advantage of quantum principles in subtle but powerful ways. Quantum theory also plays a crucial role in our understanding of the universe as a whole. The fields of quantum field theory and quantum electrodynamics describe how particles interact with fields and with one another, accounting for phenomena ranging from particle collisions to the vacuum fluctuations that permeate empty space. These theories have been confirmed to remarkable degrees of precision in experiments and are foundational to modern physics. In cosmology, ideas like quantum fluctuations in the early universe are thought to have seeded the formation of galaxies, while efforts to unify general relativity with quantum mechanics continue to drive research in quantum gravity and string theory. The influence of quantum mechanics is so pervasive that it is hard to find an area of modern science or technology that does not depend on it. From the everyday act of using a smartphone to the most advanced experiments at particle accelerators, quantum theory provides the tools and insights needed to make sense of the behavior of matter and energy. It has changed not just how we understand the microscopic world, but how we build and interact with the macroscopic one. What was once a mysterious and abstract theory developed to explain puzzling phenomena like blackbody radiation and the photoelectric effect has become the basis for entire industries. Its concepts have moved from the realm of paradox and philosophical debate into the core of applied science. And as our ability to harness and control quantum systems continues to grow, the influence of quantum mechanics on our daily lives will only deepen. In every photon captured by a solar panel, in every electron guided through a transistor, and in every atom aligned inside an MRI scanner, the principles of quantum theory are at work. Far from being esoteric, they are embedded in the world around us, invisible, precise, and essential. Quantum theory is not just a model of the world. It is the foundation upon which the technologies of the future are being built. If you're still awake, thank you for joining this journey into quantum physics. We hope you learned something new, or at least found a moment of peace. If sleep hasn't found you yet, feel free to explore another calming video on the channel. Until next time, stay curious and sweet dreams among the stars.